This is Mr. Higgins presenting for Astronomy. The key ideas or concepts in this video are going to be the Doppler Effect or shift, the Hubble Constant, the Big Bang Theory, and dark energy. The Doppler Effect, the frequency of light stretches or compresses. As photons travel through the vacuum of space, they can tell us information about faraway objects that produce light. Even if that object is billions of light years away, some of that light might make it through all the cosmic dust and make it to Earth, where we can use it to show that the universe as a whole is moving away from us. We know this due to the Doppler effect. Here we have a star emitting waves of light in all directions at once. If the star is moving in space, it will compress the light waves in the direction that it is moving, and the waves behind it will stretch out, getting further from each other. You've seen this before, but with sound. As the motorcyclist passes the observer, the sound changes, getting higher in pitch and lower in pitch, when in reality the sound coming off the motorcycle is a constant sound, just like the constant light coming off of a stable star. We have here a star, a stable star, and let's have this star moving to the left on your screen. So the energy of the star is compressed in front of the star and stretched out behind it. If you place two observers, one the star is moving towards and one the star is moving away from, both observers will see the light coming off the star slightly differently. The star is releasing white light, or a continuous spectrum, a rainbow, so we've got that black body releasing of light. The blue side of the spectrum of light is more compressed in its wavelength than the red side of the spectrum, which has more stretched out wavelength, so less energy, still moving at the speed of light. The light for observer 1 appears bluer, or blue shifted, because the light is being compressed by the movement of the star. The light for observer 2 appears redder, or red shifted, because the light is being stretched by the movement of the star. The Hubble Constant. The universe is expanding. Then in 1925, Edwin Hubble was observing a special type of star called a Cepheid variable star. Cepheid variable stars are unique because they let us measure outside of our own galaxy. They increase and decrease their brightness and color in a very predictable pattern, and all Cepheid stars go through the same pattern. When Hubble measured the Andromeda Galaxy, our nearest neighbor, using Cepheid variable stars, Hubble showed that Andromeda was blue shifted, or moving away from us. But when he measured other galaxies, he found that nearly all other galaxies were red-shifted, or moving away from us. When Hubble compared many galaxies together and plotted them on a graph, he found the average velocity of galaxies moving away from us to be about 68 kilometers per second. The Hubble Constant. We will be expanding upon this idea later with dark energy in the accelerating universe. The Big Bang Theory. The universe must have come from a single point. If nearly all galaxies are moving away from us at the Hubble Constant, that means at some point all of the matter in the universe must have been at the same location. This is the basis for the mathematics behind the Big Bang Theory. So, objects that are larger than galaxies, galaxy groups, are supporting this, because at a universal scale, a very large scale, everything is accelerating away from us. That makes the Big Bang a theory in astronomy rather than a hypothesis, because remember, in science a hypothesis becomes a theory when there's overwhelming mathematical support. So let's overview the Big Bang and how the universe formed in three broad categories. The first is the singularity, or where all matter in the universe existed before the Big Bang. And here it is. Really exciting. We would actually see nothing, because all matter didn't exist yet. Everything's in a single point, but you wouldn't be able to see it because none of the universal laws existed. So this yellow dot really doesn't represent that singularity because nothing existed before the universe. It's just the potential for something to happen. But all the energy that could exist to create our universe existed in this singular point. That's why we call it a singularity. The history of the universe still hadn't been written. And the second broad category of a universe's formation is when the universe expanded and formed its laws, and finally matter formed out of the energy represented in the singularity. In the first second, the universe inflated fast enough that when the universal laws formed, the young universe wouldn't collapse back in on itself, because if it didn't expand before the laws, gravity would make it smash back together. And electrons and protons were created in this hot soup of plasma fusing together to make the first elemental hydrogen. During the inflation period, which happened so fast you need a fancy unit to describe it called a Planck time unit, which is a really good science word, but really isn't something that you should really memorize, is about 10 to negative 43 seconds, or basically instantly. So near the end of the inflationary period, for all four of the fundamental forces, they came together and started to rule the universe, which is pretty good, because otherwise the universe would have fallen back in on itself due to gravity. Finally, the universe was cool enough to form matter, and electrons and protons came together from the fundamental quantum particles of our reality, making matter. And for around 3 minutes, the universe was hot enough to fuse protons and electrons together to make the first neutrons. Lucky for us, the universe didn't do that for very long, and so the remaining 99% of the universe was hydrogen at this point. Otherwise, there wouldn't have been enough hydrogen to make all of the stars and galaxies later, because that would be pretty important for us to exist. And so the foundations of our universe from the Big Bang took about 3 minutes for the next 380,000 years to cool down. So 3 minutes and then 380,000 years of everything cooling down. And at the very end of the time of the cool down period, so during the cool down period, we have atoms forming, and the electrons are being bumped up, and then they fall back down. Then they bumped up, and then they fall back down. So all the electrons in these hydrogen atoms are releasing light. So the foundations of our universe, about 3 minutes when everything cooled down, and then after that, that's when all the structures for galaxies in our current universe started to happen. And the first massive stars that formed were so huge that they just exploded. It was only after things calmed down even further that black holes would begin to create the structure for the universe. Galaxies would form and cluster together in their own larger groups of galaxies, and gravity would continue to provide structure to the universe, creating these vast structures and webs of galaxies, filaments of matter in an ever-expanding universe. But why is the universe still expanding? Our measurements show that it is actually accelerating, so it's getting faster, and every group of galaxies is rushing away from every other group of galaxies. Dark energy, a property of the universe, is making galaxy groups accelerate away from each other. We are not quite sure what is causing the acceleration of the expansion of the universe, but we can measure it. Our best hypothesis is that the acceleration of the universe is driven by a property of space itself. As more space is created, the vast emptiness between the galaxies, it pushes on the fabric of reality, causing large structures like galaxy groups to continue to accelerate away from each other. So more space is being made, meaning it's pushing harder, and so the galaxies push more away. We are very confident on how matter interacts, because we can see gravity and measure it. And we know that dark energy must exist, but it's not explained by our current models. So what we're trying to figure out is the connection between our matter interactions, our gravity interactions, and why dark energy, which we can only measure, we can't do anything but observe what it's doing. Well, that's the next big step in astronomy. That's what a lot of astronomers are interested in studying in the future and are studying right now. This has been Mr. Higgins, so y'all have a fantastic day, and that blah 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 YouTube and Facebook stuff, go ahead and subscribe, blah blah blah. Yeah.